Section 7.4, Integration by Partial Fractions. When dealing with fractions, we often try to combine everything into one big fraction with a common denominator. However, in practice, when integrating, this can actually be a little bit hurtful to us because it just makes one big messy fraction to integrate, whereas if we have lots of little fractions that are simple, then integrating can usually just be done with the reverse power rule. So what we're going to try to do in this section is just split up fractions using partial fractions. Our first step every single time is going to be to look at the degree of the numerator polynomial versus the degree of the denominator polynomial. If the degree of the numerator is greater than or equal to the degree of the denominator polynomial, then we will always divide first and then see if we still need to split. So let's start using log division for x cubed plus x divided by x minus 1. We'll take x minus 1 and put it inside x cubed plus 0x squared. We'll use a placeholder plus x. So then taking x cubed and dividing by x, we get x squared. And then we multiply and get x cubed minus x squared for x squared times x minus 1. And then we subtract. So we get x cubed minus x cubed is 0. X squared minus minus x squared is positive x squared. And we bring down the x. So then we repeat divide, multiply, subtract, bring down. So we divide by x and we get x. We multiply and we get x squared minus x. We subtract and we get 2x. And there's nothing to bring down. So we divide again. 2x divided by x is just 2. We multiply and get 2x minus 2. We subtract, and we just end up with 2. So it looks like we have x squared plus x plus 2 with a remainder of 2. So now we can rewrite our integral. So we'll say that the integral of x cubed plus x over x minus 1 dx is equal to the integral of x squared plus x plus 2 plus our remainder of 2 over our quotient of x minus 1. So that's a little bit more to write, but it's way easier to integrate because now we can just say the antiderivative of x squared is x cubed over 3. For x, it's just x squared over 2. For 2, it's just 2x. And for 2 over x minus 1, it's just the absolute value of the natural log of x minus 1. And we keep our plus c. Okay, in this example, the degree of the numerator is not greater than or equal to the degree of the denominator. So instead of dividing, we'll go straight to trying to figure out what the partial fraction decomposition of this rational function is. So in order to start doing that, let's factor the denominator. So 2x cubed plus 3x squared minus 2x is equal to x times 2x squared plus 3x minus 2. Just factor out x. And then we could factor that quadratic and get x times 2x minus 1 times x plus 2. So this means that x squared plus 2x minus 1 over x times 2x minus 1 times x plus 2 is what our original integrand is, and we're going to rewrite that as something over x, some number over x, plus another number over 2x minus 1, plus another number over x plus 2. We write a term over each of our linear factors on the top, where the coefficient is 1 degree lower than the denominator. So all of our denominator terms are linear, so all of our numerator terms are constant. If our denominator terms were irreducible quadratics, like let's say we had x squared plus 1 on the bottom, then we would have to have a linear term on the top. We'll do examples of those soon. So we write a different fraction for every possible factor that we have. And we write repeated factors when we have repeated factors in our denominator, which we don't have in this case. So let's see if we can figure out what these numbers a, b, and c would have to be to make this equation true. So we write x squared plus 2x minus 1. And instead of dividing by this, how about I multiply the left and right side of the equation by that denominator? So then that'll cancel out this denominator. It'll cancel out the x, it'll cancel out the 2x minus 1, and it'll cancel out x plus 2. And it'll leave me with whatever did not cancel for each on the top. So that means it'll leave me with 2x minus 1 and an x plus 2, because the x canceled for a. And then for b, it leaves me with x and x plus 2, because the 2x minus 1 canceled when I multiplied. And for c, I'm just left with x and 2x minus 1. So then what I can do is I can FOIL this out, and I can distribute, and I can distribute, and then I can group together all of the terms that have an x squared in them. So then I'll write all of those together, and I get that there's 2a x squared terms, and there's a b x squared term, and there's 2c x squared terms. So I factor the x squared out of all of those, so that I have a coefficient on x squared now. I do the same thing with all the x terms. I can see that there's going to be 3a x terms, and there's going to be 2b x terms, and minus c. So I factor out that x. And then I look at all the constant terms, and it's just minus 2a. Notice on the left side I have a quadratic. On the right side I have a quadratic now, because all of these are just, numbers. So this is just something times x squared, something times x minus something. So because these are both quadratics, they must match. So this something x squared must match with this 1 x squared. So that means that the coefficients must be equal. So 2a plus b plus 2c must equal 1. Similarly, this something times x must equal 2 times x. So we must have the 3a plus 2b minus c is equal to 2. Lastly, we must have the constant term equals the constant term. So we must have minus 2a is equal to minus 1. So let's see, that immediately gives us what the value of a is. If minus 2a equals minus 1, then that means that a is equal to 1/2. So we can plug back in for a, and if I take the second equation, this one, and I multiply it by 2, then I get 4b minus 2c. So if I take that and I add it to the top equation, so then this becomes 6 times 1/2, which is 3. 3 plus 1, because multiplying a by 1/2, so that's 4 plus 5b, and then the c is canceled, so that equals 5. So 4 plus 5b equals 5, so b is equal to 1/5. And then I can plug back in, and I can see that c is equal to minus 1/10. Okay, so now I think we can rewrite our integral. So we get that the integral x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x is equal to the integral of, well, it's a over x. We said a is a half, so that's half over x. So I'll just write half next to 1 over x to make this easier. Same for b over 2x minus 1. b is 1/5, so it's 1/5 times 1 over 2x minus 1. And then c was minus 1/10. So we have that times 1 over x plus 2. And then we just take antiderivatives. So this is half ln absolute value of x plus 1/10 ln absolute value of 2x minus 1 minus 1/10 times ln of absolute value of x plus 2. And I already used the letter c, so how about I use k for my arbitrary constant. Okay, so again, for this example, our degree of our numerator is not greater than or equal to our degree of our denominator, so we do not divide. Instead, we just rewrite our integrand, 1 over x squared minus a squared, as 1 over x minus a times x plus a. And we're going to find some partial fractions, a over x minus a, and we're going to find another coefficient, b over x plus a. Came out a little sloppy. Okay, so we're going to multiply the left and right side of this equation by x minus a times x plus a to eliminate the denominator. So we'll get, just flipping left and right, we get a times x plus a plus b times x minus a equals 1. And what you could do is distribute and equate the coefficients as we did in our previous example, but how about we use another method to solve this? This is an identity, so it must be true for every possible value of x. So that means that I can plug in any x, it must still be true, so let's plug in some convenient values that allow us to solve for a and b. Notice that if I plug in x equals a, then that eliminates this term entirely because a minus a is 0. So all I have left with is a times a plus a, which is a times 2a, equals 1. So that means that a must equal 1 over 2a, because a must have the same value no matter what x I plug in. So if a has the value 1 over 2a at x equals a, then a always has the value 1 over 2a. And similarly, if I plug in minus a, then that tells me pretty quickly that b times minus 2a equals 1, so b is equal to minus 1 over 2a. You could even solve the system in the previous example by this method. If I plug in a convenient value for x, notice 0 is a convenient one because that kills off these two guys, and then you would just be left with this term to solve for a. Minus 2 is another very convenient one because if you plug in minus 2, then that eliminates this one, and you're just solving for c. And once you have, a and c, then you can go back and solve for b or whatever you'd like to do. You can even plug in half to cancel that if you want, and then that cancels this too, and then you solve for b. But in any case, let's return to the example we're actually doing. So we figured out what a and b are, figured out what our coefficients are, so now we can rewrite our integral. So dx over x squared minus a squared is equal to 1 over 2a, because I'll just factor it out there in both. And I'm left with the integral of 1 over x minus a minus 1 over x plus a. That's the same as if I put 1 over 2a as this coefficient, and minus 1 over 2a is this coefficient, and then I just factored out 1 over 2a. So we take antiderivatives. We get 1 over 2a times the natural log of the absolute value of x minus a minus the natural log of the absolute value of x plus a. And that's 1 over 2a times the natural log of x minus a over x plus a by laws of logarithms, because the difference of logarithms is the quotient in a single logarithm. So this is kind of a cool formula. Now we have a formula for the integral of 1 over x squared minus a squared, and that equals this mess. So we'll probably use that later. Notice in this example, the degree of the numerator is greater than or equal to the degree of the denominator because it's 4 versus 3. So we'll start by dividing. We've got x cubed minus x squared minus x plus 1, and we want to fit that into x to the 4th plus 0 x cubed minus 2x squared plus 4x plus 1. Almost made it. So we take x to the 4th divided by x cubed, and we end up with x. So we divide, then we multiply, so we get x times x cubed is x to the 4th, then times minus x squared is minus x cubed, and we keep going, minus x squared plus x. And then we subtract. And we get x cubed minus x squared plus 3x plus 1, because we bring down the 1. And we divide again. X cubed divided by x cubed is 1. We multiply, we get x cubed minus x squared minus x plus 1. And we subtract. We get 4x. So it looks like x to the 4th minus 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1 is equal to x plus 1 plus our remainder 4x over our quotient x cubed minus x squared minus x plus 1. Okay, all that's left for us to do is factor our denominator. That way we can write partial fractions. So let's see, we've got x cubed minus x squared minus x plus 1. I can take the left side and factor it separately from the right. So I get x squared times x minus 1. And then I factor out a negative 1, and I get negative x minus 1. So factoring by grouping, I get x squared minus 1 and x minus 1. And x squared minus 1 becomes x minus 1 times x plus 1 times x minus 1. So notice there's a repeated x minus 1 term. So I'll write that as x minus 1 squared. And I'll leave the x plus 1. So this repeated term means that when I do my partial fraction decomposition, I have to write a separate fraction for x minus 1 and a separate fraction for x minus 1 squared. So I get 4x over x minus 1 squared times x plus 1 is equal to a over x minus 1 plus b over x minus 1 squared plus c over x plus 1. Notice I'm not worrying about this right now. I'm on, because that's easy to integrate. Integrating x squared over 2, integrating 1 is just x, but integrating this is the pain, so this is the only thing I'm bothering decomposing. So multiplying through by the denominator, we get 4x is all that's left on the left, and we get a times x minus 1 times x plus 1, because one of the x minus 1's cancel, so I have 1 left, and then b times x plus 1, and then c times x minus 1 squared. So how about we keep going? We FOIL everything, and we distribute and then multiply through, and we see that we have an ax squared term and a cx squared term, so we have a plus c times x squared when we group together all of our x squared terms and factor. Similarly, we have b minus 2c times x, and we have our constant term as negative a plus b plus c. So what we'll do is we'll equate our coefficients. Notice there is no x squared. So we just end up with a plus c is equal to 0. And then we've got b minus 2c is equal to 4, because there is a 4x. And there's also no constant term, so this last term must also be 0. So we have minus a plus b plus c is equal to 0. Okay, so let's see what this tells us. We've got b, if we take these two equations and we add them together, then we have b plus 2c equals 0. So that means that b is equal to minus 2c. So we have minus 4c equals 4, so that tells us that c is equal to minus 1, which means that a must be equal to 1 by using the top equation. So then means we can figure out that b is equal to 2. So now we know what our coefficients are. Let's try writing our integral. So x to the 4th minus 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1 becomes the integral. Let's see, what did I do? We said it was x plus 1 plus this whole mess that we just decomposed. So that means my integral becomes x plus 1 plus a over x minus 1. And we said a was 1, so that's 1 over x minus 1. Plus b is 2, so 2 over x minus 1 squared. And then minus 1 over x plus 1. So that's easy to take antiderivatives. We get x squared over 2 plus x plus ln of x minus 1 with the absolute value. And then over here we could do a mental u substitution. If we let u equal x minus 1, then when we integrate we get 1 over u squared, so that's minus 1 over u, so this will be minus 2 over x minus 1 minus ln absolute value of x plus 1 plus some constant. We'll use k because we use c. So we can rewrite that a little bit. We get x squared over 2 plus x minus 2 over x minus 1 plus the natural log of x minus 1 over x plus 1 plus k, using laws of logarithms. For this next example, we're going to need this integral over here. So if you want to prove this real quick, you notice that taking the derivative of tangent inverse, if it's tangent inverse of x, it's 1 over 1 plus x squared. So this would be just a chain rule problem. You do 1 over 1 plus x squared over a squared times the derivative, which is 1 over a, and then 1 over a and 1 over a gives you another 1 over a squared, which cancels with the a squared in the denominator, and you just get 1 over x squared plus a squared. So differentiating this side gives you the left pretty quickly if you know that the derivative of tan inverse is 1 over 1 plus x squared. So let's use that by taking a look at this problem. Notice the degree of the numerator is not greater than or equal to the degree of the denominator. So we do not divide. Instead, we'll just go straight to factoring our denominator. So we see that x cubed plus 4x is equal to x times x squared plus 4. So that means that we're looking at 2x squared minus x plus 4 over x times x squared plus 4. Because x squared is plus 4 is a sum of squares, we can't factor it any further. So we'll rewrite this as a over x. And then for our second term, it's an irreducible quadratic. We couldn't factor this anymore. Because it's not a linear term, the top does not become a single coefficient. It becomes a linear term. So we end up with bx plus c. We have to have 2 new numbers to solve for. So that means that when we multiply the top and bottom, when we multiply the left and right by the denominator, we end up with 2x squared minus x plus 4 equal to a times x squared plus 4 plus bx plus c times x. So let's group together all of our x squared terms. We get a plus b times x squared. And we group together all of our x terms. We get c times x. And just 4a is all that's left. So that means that a plus b must equal 2. So we get a plus b is equal to 2. I should actually leave a space for c. And we get that c is equal to minus 1. Oh, it's a freebie, great. And we get 4a is equal to 4, which is basically another freebie. So the last equation tells us that a is equal to 1. And then that means that b is equal to 1 also. And c was given to us as minus 1. So we can rewrite our integral now. So we said it was a over x plus bx plus c over x squared plus 4. So that means that 2x squared minus x plus 4 over x cubed plus 4x becomes the integral of 1 over x plus x minus 1 over x squared plus 4. And that's going to be equal to the integral of 1 over x dx. And then we would like to take advantage of this formula that we talked about earlier. So how about we split off the 1 and the x? So I'll write this as the integral of x over x squared plus 4. And I'll rewrite the other one as the integral of 1 over x squared plus 4. So then if we have x squared plus a squared, that means that a is 2. So that resolves this integral pretty quickly. And in the other integral, you might be saying, hey, that looks terrible also, but it's actually not that bad. It's a pretty straight u substitution. Whenever you've got something where the derivative is inside of the integral also, then, it's just classic, let u equal the thing that you want to take the derivative of. So x squared plus 4, then du is equal to 2x dx. So that means that your integral becomes half the integral of 1 over u, which is just half ln absolute value of u. So that means that we just get ln of absolute value of x plus half of ln of the absolute value of x squared plus 4. But x squared plus 4 is always positive, so it's just x squared plus 4. And then minus half of, using our formula over here, it was 1 over a, x over a is 2, so minus half tan inverse x over 2, and our constant. Okay, so in this case, it looks like the degree of the numerator is greater than or equal to the degree of the denominator, so we'll divide first. When we do the long division, which I'm not going to write out this time, we get 4x squared minus 3x plus 2 divided by 4x squared minus 4x plus 3 is equal to 1 plus x minus 1 over 4x squared minus 4x plus 3. Notice that in the denominator, if I look at the discriminant b squared minus 4ac, that's negative 4 squared minus 4 times 3, then that's equal to negative 32, which is a negative number. It's less than 0, so that means that there are 0 real roots, so we can't factor this. So if we can't factor it, we can't use partial fractions. So we're going to have to figure out another way to do our integral. So instead, how about we try to complete the square for the denominator? So we'll take 4x squared minus 4x plus 3, and we'll write this as, well, to complete the square, we need something squared minus something times that variable. So in order to come up with a variable squared, how about we just use 2x and square that? Because that's 4x squared. And then minus 2 times 2x plus 3. So we'll pretend that our variable x is really 2x in this case, and write this entire quadratic in terms of 2x instead of in terms of x. And then completing the square, we get 2x squared minus 2 times 2x. Since this is the coefficient now, we'll add half of that and square it, so that's plus 1. Then we added 1, so we have to make sure to subtract 1 to keep our equation balanced. And that's just equal to 2x minus 1 squared plus 2. So we can do a u substitution. How about we let u equal 2x minus 1, since that'll make this just u squared plus 2. So then du is equal to 2 dx. We need to know what x is equal to, though, because there's still an x minus 1 up here. So how about we let x equal, let's see, u is equal to 2x minus 1, so we'll add 1, we get u plus 1 is equal to 2x, so x is equal to half of u plus 1. So then our integral, 4x squared minus 3x plus 2 over 4x squared minus 4x plus 3 is equal to 1 plus x minus 1 over 4x squared minus 4x plus 3, assuming you did your long division correctly. And then we'll take antiderivative of 1, because why not? We'll get x. And then for our other integral, let's see, we've got du equals 2 dx, so dx is half du. And then x minus 1 is equal to half u plus 1 minus 1. And our denominator, like we said, that's 2x squared, that's 2x minus 1 squared plus 2. U is 2x minus 1, that's why we chose it. So we just get u squared plus 2. So that's x plus, well, how about I take half and I factor it out of the numerator. So this half comes out easily, and then that half comes out over there and leaves me with 2. So I have outside 1/4 now because I factored out a half, and inside I have u plus 1 minus 2. So that's u minus 1 over u squared plus 2. So this means that I've got x plus 1/4 u over u squared plus 2 minus 1/4 of 1 over u squared plus 2. So this guy looks like an easy u substitution because I have the u in the numerator, and this guy looks like a tan inverse candidate. So I get x plus 1/8 because when I do the mental u substitution for, well, not really u, I have to use, I guess, t or something. For t equals u squared plus 2, then the derivative dt would be 2u du. So solving for that, I get half. And I have natural log of u squared plus 2. Again, I don't need the absolute value because u squared plus 2 is always positive. Try taking the derivative here. You could see that you get back over there. And then I've got 1/4 1 over, actually, let me just take the derivative. 1/4 times 1 over rad 2 tan inverse of u over rad 2. We just use the formula that we just talked about. So that's x plus 1/8 ln of, let's see, u squared plus 2. So we let u equal 2x minus 1. So to square that, we get, u squared plus 2 is this. So that's this. So we're just right back where we started. So we'll plug that back in. 4x squared minus 4x plus 3. And then minus 1 over 4 rad 2 tan inverse of u over rad 2. U is 2x minus 1. So we are done. As we saw earlier, sometimes you can have a partial fraction decomposition where you have irreducible quadratic terms in your denominator. Each of those requires a linear term in your numerator. So let's do a little bit more practice with these cases. How about we try writing out this partial fraction decomposition? I'm going to be lazy now and not rewrite the entire quotient that you see because it's just too much. So I'll just write the decomposition. My first term is x. So that's my first factor. So that means I'll have a over x. Then my next one is x minus 1, which is still linear, so I just need a b. Then my next one is x squared plus x plus 1. You can calculate the discriminant to see that that's irreducible. So this must need a linear term in the numerator, so I'll put cx plus d. Then my next term is another irreducible quadratic because it's x squared plus 1. So that means that I need more letters. How about I use ex and f? And then, well, e and f and I multiply by x, but you get the idea. My next term, remember, we have to write a separate fraction for each time that our irreducible term was repeated. So it was repeated 3 times, so I need an x squared plus 1 squared term, and I need an x squared plus 1 cubed term. So that means I need more letters. I'll use G and H for my x squared plus 1 squared term, and how about I use I and J? So you could see that even though this would be horrible to actually do in an example, it is technically possible if you spent enough time and you split them up into each of these individual terms. You could potentially solve for all of these different coefficients, maybe use a calculator to solve a matrix or something, and then you would go and write the decomposition and integrate term by term by term. So let's do a slightly less unpleasant example, but still not pleasant. So we'll take a look at 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 squared. So we have an x, so that means I'll write a over x because of our denominator. And we also have an x squared plus 1 term, so that's irreducible. So I need bx plus c over x squared plus 1. But I have another irreducible term because it's a square. So I'll need dx plus e over x squared plus 1 squared. So we multiply left and right side by the denominator. We get negative x squared plus 2x squared minus x plus 1 is equal to a times x squared plus 1 squared plus bx plus c times x squared plus 1 plus dx plus e times x. So that equals a times x to the 4th plus 2x squared plus 1 plus b times x to the 4th plus x squared plus c times x cubed plus x plus d times x squared plus e times x. When we keep going, and we get a plus b times x to the 4th by grouping together all our x to the 4th terms. And we group together all of our cubed terms, we get cx cubed. Group together our squared terms, we get 2a plus b plus d times x squared. And we get c plus e times x. The parentheses confuse me, so I made it look like a c because I'm bad at drawing. And we get no x to the 4th terms, so mercifully a plus b is equal to 0. Oh great, so c is equal to minus 1. And we get 2a plus b plus d is equal to 2. Then c plus e is equal to minus 1. And a is equal to 1. Okay, so if a is 1, that's one of them. Then b by the first equation must be equal to minus 1. C they gave us was minus 1. So we just, to figure out what d is, we can use this equation, because we know what a and b are, to see that d is equal to 1. And since we know what c is, this equation tells us that e is 0. So we can rewrite our integral now. Our integral 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 squared becomes the integral of 1 over x minus x plus 1 over x squared plus 1 plus x over x squared plus 1 squared. Because when we split it, we said that it was a over x, bx plus c over x squared plus 1, and dx plus c over x squared plus 1 squared. And now that we know what those coefficients are, we just plug them in. So we get the integral of dx over x minus the integral of x over x squared plus 1. And I'll separate off the 1 over x squared plus 1. Since the negative is multiplying both, I'll write it also for the x squared plus 1 integral. And I just have one integral left, x over x squared plus 1 squared. Okay, so it looks like because there's an x term on the top over here, I can just use a u substitution for that guy. And again, x over there, so I can use a u substitution for that guy. So let's let u equal x squared plus 1. We can do this in our head, I think, and get ln absolute value of x minus half ln x squared plus 1 minus tan inverse of x for this guy, and then minus 1 over 2 times x squared plus 1 plus constant k. Okay, so we spent a lot of time integrating rational functions, but sometimes you have a square root function. And if it's something like this, where we don't necessarily want to use trig substitution, you would probably want to use u substitution, which can then turn your integrand into a rational function where you could then use partial fractions. So to see this, let's let u equal the square root of x plus 4. Then u squared, so that we can get rid of the square root, is just x plus 4. So we can solve for x now and see that x is u squared minus 4. And now we can see that dx is 2u du. Notice you didn't want to get dx right off the bat, because differentiating square roots is never as fun as differentiating squares. So now we can rewrite our integral. The square root of x plus 4 over x as the integral of u over u squared minus 4 times 2u du. So that's just 2 times the integral of u squared over u squared minus 4, which is 2 times the integral of 1 plus 4 over u squared minus 4 du. And we just get that by doing a quick division, because notice at this point the degree of our numerator is greater than or equal to the degree of our denominator. And that's the first step to solving any of these problems with rational functions, is you look at the degrees of your numerator and denominator. So then that becomes 2 times the integral of du plus 8 times the integral of du over u squared minus 4. So that's one of those is easy, it's just 2u. The other one, I think we did. Let's go back really quick. Yes. Notice we figured out what the integral of 1 over x squared minus a squared is. So we can say what the integral of 1 over u squared minus 4 is. That's just if a is equal to 2. So that we solved and we saw it was equal to 1 over 2a ln of x minus a over x plus a. So it'll be 1 over 2 times ln of x minus 2 over x plus 2. So let's go back and plug that in. Whee! got a little carried away. We get 2u plus 8 times 1 over 2 times 2 times ln of u minus 2 over u plus 2 by example 3. And this is just 2 times the square root of x plus 4 when we substitute back, plus 2 times ln of square root of x plus 4 minus 2 over square root of x plus 4 plus 2 plus c.